So we were there yesterday, right? At this point where we said, okay, we had to do an interpolation, okay, in order to find your d bars more accurately, correct? So if you really think about it, right? Think about it as something like this mouse, let's say. Okay, so suppose you had this mouse, and if you're kind of say translating it, right? You keep the mouse on a Z stage, and then if you translate it, and then each time, okay, you take a picture. Now, what will really happen is, of course, this is more or less vertical, but then imagine something like an object, right, which has a varying depth. So then, what would happen is every time you move by delta d, there'll be a rim of points, right, which will anyway hit the focal plane, right, because some point, right, may have kind of overshot, but there'll always be some rim that will be in focus. But then the number of such rims, if you really look at it, is simply the number of frames that you plan to capture. Now, the rest of the points are all actually out of, in the sense that they have not hit the focal plane at all. So in that sense, there is really a motivation to look for a d bar which is more accurate, because otherwise, what is going to happen is you will simply have n rim, right? N point, whatever, n such points on the, not n points. You will have like n such rims, and those are all the points that will likely be in focus, in the sense that they are exactly hitting the focal plane. Everything else is not, right? So that is another way to kind of look at the motivation for really doing this interpolation, because for all the other points, they were all kind of either they have undershot or they have overshot, right? And so, which means that your d bar could be, actual d bar could be more than the thing, right, that you are expecting, or it could be just less, right? Now, so I just wanted to go through this interpolation today, okay, and then if time permits, right, we should also look at what are all the different focus operators, right, that we can use. All right, so yesterday, right, I started by writing down the equations for fm plus 1 and fm minus 1, which is like a Gaussian fit. So if you just write down ln of f, okay, so if you go back and do ln of fm, okay, then we'll get ln of fp. These are all very simple things, but we'll just going to see, we'll still work through them. D bar whole square by 2 sigma square. Ln of fm plus 1, and doing a Gaussian interpolation, other than the fact that, right, it will actually give you this d bar, hopefully, which is much more, which is actually better than your dm, okay, that where you think the maximum is occurring based upon the focus measure. The other thing is that it will also tell you, it will also give you a certain level of assurance about the d bar itself. No, there could be cases where you feel that this d bar that you computed is really not so great, and you might want to bank on something else. Okay, I'll tell you what that means. So this Gaussian fitting is not only to get your d bar, but it is also to throw some light upon how good is this value of d bar, whether we can actually trust this value, whether we can use it or not, and so on. Okay, so that is also the reason why you get this fp, and you also solve for sigma, and I'll tell you, right, how you can interpret those. Okay. So ln of fm plus 1 is again ln of fp minus dm plus 1 minus d bar by 2 sigma square, and then finally ln of fm minus 1, if you look at that is equal to ln of fp minus dm minus 1 minus d bar the whole square by 2 sigma square. Okay, and then we'll just do a small sort of a manipulation here. So just do ln of fm minus ln of fm plus 1. Okay, so that will knock off your fp and you'll get dm plus 1 minus d bar the whole square minus dm minus d bar by 2 sigma square. Right, and let's also do ln fm minus fm minus 1. Ln fm minus ln fm minus 1. So that will give you dm minus 1 minus d bar the whole square minus dm minus d bar the whole square by 2 sigma square. Or in other words, what this means is that okay, we'll also knock off sigma now, okay, because right now we are only interested in d bar, right? So 1 by 2 sigma square is equal to ln of fm minus ln of fm plus 1 upon dm plus 1 minus d bar whole square minus dm minus d bar square, and this we know is also equal to, so if you look at whatever, right, call this equation 1 and 2 or whatever, and from 1 and 2, right, clearly 1 by 2 sigma square equals ln fm minus ln fm minus 1 upon dm minus 1 minus d bar square minus dm minus d bar square, right? So if you see finally, okay, so we can even knock off sigma now. So all that we have read. So now we have this equation now which involves only d bar. So both sigma and Fe have gotten out. Right. So now if we simply expand, okay, the lower one, okay, so okay, simply this kind of this one denominator. So what do you get? So if you expand it, you get d square m plus 1 minus 2 d bar d m plus 1 plus d bar square minus dm square plus 2 d bar dm minus d bar square, right? So this denominator d bar square sort of gets cancelled out and you are left with this. And similarly, if we take this denominator, we will have d square m minus 1 minus 2 d bar dm minus 1 plus d bar square minus dm square plus 2 d bar dm minus again d bar square. So here also, so the d bar square, right, will cancel off. Therefore, what we are left with is really ln of fm minus ln of fm plus 1 into, if I cross multiply, right, so what do we get? D square m minus 1 minus d square m plus 2 d bar, okay, plus 2 d bar dm minus dm minus 1 on this side is equal to ln fm minus ln fm minus 1. Okay, on this side it will be d square m plus 1 minus d square m plus 2 d bar dm minus dm minus 1. No, dm plus 1. Dm minus, here it is dm minus dm minus 1, it is dm minus dm plus 1. So we know that dm minus dm minus 1 is simply, okay, delta d, right? M minus dm minus 1 is m minus 1 delta d, dm is m delta d. So delta d, dm minus dm plus 1 is minus delta d, right? Therefore, what we have is ln fm, go down a little bit, ln fm minus ln fm plus 1 into d square m minus 1 minus d square m plus 2 d bar delta d into ln fm minus ln fm plus 1. This is equal to, on the right hand side, ln fm minus ln fm minus 1 d square m plus 1 minus d square m plus 2 d bar delta d, oh no, minus 2 d bar, because that's minus delta d, right? So this will become minus 2 d bar delta d ln of fm minus ln of fm minus 1. Okay, therefore, if you just club terms that are involving d bar, okay, so in this, if you think about it, all these quantities are known, right? Fm we know, fm plus 1, dm minus 1, everything we know, actually delta d, everything we know except d bar. So d bar, so if you club, so d bar, okay, 2 delta d, right, d bar, if you take that out as common, and then if you pull this ln fm right to the left, then you will get 2 ln fm minus ln fm plus 1 plus ln fm minus 1, right? If you if you pull everything onto the left side, so 2 ln fm, oh yeah, 2 ln fm, because this ln fm will come to the left, and then plus ln fm minus 1 minus ln fm plus 1, this is equal to ln fm. Well, you can simplify this further, but that's okay, I think. D square m plus 1 minus d square m, then let's push that out here, minus ln fm minus ln of fm plus 1 into d square m minus 1 minus d square m, right? Or in other words, we can say that we can get your d bar by simply dividing this whole guy by 2 delta d, right? If I bring this thing down, so 2 delta d, 2 ln fm minus ln fm plus 1 plus ln fm minus 1, right? If I remove all of this, right? So 2 ln fm minus ln fm plus ln 2 delta d, right? So if I remove this and shift it all to the left, then what I'm left with is really the d bar equation, and which looks like that. Right? I mean, straightforward. Okay, no great surprises there. ln fm minus d square m minus 1 minus d square ln fm minus ln fm plus 1. I'm just checking whether everything is okay. True ln fm plus, oh, there is a minus ln f minus 1. What did I? Yeah, this should be minus ln fm minus 1, right? Because this minus of minus plus, no? So this should be minus, right? Because here this 2 delta, so we have this guy, no? 2 delta d, so this is minus, so this minus and minus plus, therefore you are pulling it to the left, no? So that will become minus. So it's correct, no? Should be minus ln fm plus 1 minus ln fm minus 1. Is it okay? Right, so except for that sign, everything else was okay. And then, which also means that, means one thing is that d bar and delta d, right, will not get knocked out, because even if you do sort of, a distributive thing and all, dm plus 1 plus dm plus 1 minus dm, or even if you write, delta d will not get knocked out, okay, it will still remain. And one might also be interested, like I said, right, one could also be interested in sigma square, right. So because that also gives you, so I'll tell you what you might want to use sigma square for. So the expression for sigma square, I'll simply write it down here, okay, you already have it there, so simply following from there. So sigma square is equal to dm d bar square minus dm minus d bar square upon 2 times, you can use either of the two, right, I am just writing one of them, ln of fm minus 1, and then you can also use the very first expression that you wrote for fm in terms of fp, use that to get your fp. fp is equal to fm upon e raised to minus of dm minus d bar square by 2 sigma square. Okay, so what this means is that we can get, so we can solve for d bar first, and then we will also look for what is the value, right, that we get for sigma, and what is the value that we get for fp. Okay, now the way these other two things are actually used, right, is as follows. So sigma is something like a spread, right? So we try to fit this Gaussian, and it is giving you a sense of the spread. Now, what would it mean if you had a sigma that was large? How would you kind of interpret that? Let us say that it gives out a sigma that turns out to be large. So how would you interpret that? I mean, so it will actually mean that instead of having a very sharp curve, right, you're going like, right, it's more or less, so it's not flat, but it has a large sigma, right. So what it would mean is your ability, see, ideally, right, what you would like is a sigma that is small. because then it would mean that something has come into sharpness, and then immediately on the as you go to the left or to the right, it's falling off, right? That means your ability to say that that's where things are focused is actually is quite good. Then that that's exactly it's peaking, and then on either side it's falling off pretty abruptly. Whereas if something is like flat or close to being flat and is slowly varying, then it means that your own ability to tell exactly in which frame it is coming into focus. I mean, you may still get some value, for some frame where you find that it is high, it is the highest. But that doesn't mean that you are kind of very sure now, because it would simply mean that your texture itself is such that, so if you go back to that stack, right, that we've been drawing, so what it could mean is that you are probably looking at a region which is not really so active, or which is probably the underlying image intensities are not really that very active, because of which when you right, even when you sort of translate and then right you capture these multiple frames, it is saying that the variation, the blur, you're not able to sense it much, and therefore your own ability to tell. So what it would mean is that having some kind of a curve like that versus some kind of a curve like this, right, you would rather go for this, because here things are falling off pretty quickly, whereas here, right, when this looks like this is a peak, but then how do I know? Okay, so it could also be that this also are probably quite close to the peak, and therefore sigma is something that we look for. And then if we find that sigma is, again, right, where we draw a line and say that the sigma is high enough, right, depends on the experiment. But if we find that sigma for some points is relatively coming out to be much higher than for, let's say, sigma at other points, then that is an indication that the image is probably lacking enough information in those particular locations. And therefore you could either go with the d bar that you have computed from here and still hope that you're not probably going too wrong, or the other way to do it is you kind of look around and then see, kind of ignore this completely and just look around and see what d bar have come around it. And if you're lucky, and let's say this region is bad, but then the adjacent regions are not so bad, therefore you have a more sort of a confident d bar there. Confident again in the sense that those sigmas are not really that big and so on, and therefore you would just want to maybe replace this guy with that d bar, because anyway we kind of make an assumption that things are locally smooth. I mean, we don't expect, of course, you could go wrong if you're sitting on an edge and so on, but because you're not going to be always sitting on an edge, so you could simply borrow on the fact that things, neighbors should look alike, and therefore, right, instead of using this, I would still bank upon just picking some d bar resistance. You can take the median of the neighbors, or take the average of the neighbors, or something more sophisticated can be done. I'll talk about it later, what is called a tensor voting. But let's say the simplest thing that you could simply do is take the average of the median of the neighbors and just copy that d bar at that location. Okay. And FP is again another thing that is also good, because what can happen is, imagine that, right, at some at most locations, okay, you get a nice kind of right, I mean, nice kind of a bell curve. So this is like this is your DM, and then about which, right, you have this curve. Now at some places, right, you may still get this kind of a curve, but then it could be something like that. Now, which means that your peak itself is very low relative to, let's say, the kind of FPs that you've been able to get elsewhere in the images. There are some portions where your FP is turning out to be very small. Your sigma may be still okay, but then FP itself is very small. In which case, again, right, you may not want to probably take that, and you would then go scout for some d bar in the neighborhood and simply use that. Okay, so in that sense, the sigma and FP are actually useful. So when you actually copy that d bar value, so each time when you do the copying, you're sort of more sure that what you're copying is hopefully a good value. Okay, because these can be noisy, right? See, the whole strength of this particular method is that it can be done, right, simultaneously. It's a parallel kind of a scheme, right? So it's a parallel scheme in the sense that, right, you can operate at one pixel independently of the other. But then, right, that also means that you could have trouble, because you're not enforcing some kind of smoothness. You're not saying that right, if this guy carries a value d bar, then the other guy should have a value close to it. Right? You're not saying that. So which means that you can suddenly see some spikes in your plot, right? That is simply because of the fact that the image is lacking some texture right underneath and so on, and therefore, right, you could get, and you would think that, I mean, and generally nature does not have whatever scenes like that, where you have a sudden spike coming out of a kind of, right, a 3D scene, right? So So you can get, so you can do a kind of a post processing, or else you can take this depth map and then do some kind of post processing. But all those are kind of ad hoc then, right? What kind of post processing you do and so on. So hopefully, if you have a textured image, you won't have any issues. But then that you can't guarantee, right? In a real scene. Okay. Anything that you want to ask prior to going to those focus operators, right? Which are supposed to do this job now.